This is my talk called The Fastest FizzBuzz in the West. My name is Dustin. I'm DI on GitHub. I work for a company called PromptWorks, so we're a consultancy. We have offices in Philly, New York, and here in Austin. I might look familiar because I'm also a PyTexas organizer, so I'm the program chair, and sometimes that means filling in for people who can't come and give their talks. So the original speaker is supposed to be here, had a family emergency, and so I'm stepping in and giving you guys this talk. And like I said, it's called The Fastest FizzBuzz in the West. So first things first, this talk is not about FizzBuzz. Actually, bear with me for 1 second. I need to get my speaker notes up. Okay. All right, awesome. So first things first, this talk is not really about FizzBuzz. However, FizzBuzz is kind of like the faux motivation for this talk, right? So to get started, I actually need to explain FizzBuzz to you all. So who knows what FizzBuzz is? Who's never heard of FizzBuzz before? And who's been asked FizzBuzz in a job interview before? Really? Awesome. Okay, cool. All right, so for those of you that don't know, this is the FizzBuzz problem. It's a pretty simple little programming problem, and people use it sometimes in interviews to sort of weed out people that can't program at all. So the idea is that you write a program that prints the numbers from 1 through n, and if the number is divisible by 3, instead of printing 3, you print the word fizz. If the number is divisible by 5, instead of printing the number 5, you print buzz. And if it's divisible by both 3 and 5, you print FizzBuzz. So if you printed from 1 to 15, 15 instead would be FizzBuzz. So I've never actually been asked to do this in a job interview. But at various stages of my programming career, I've always kind of imagined what I would do if someone did ask me it. So really early on, when I was kind of first learning Python, I would have probably written something like this. And this is sort of like the most naive approach to FizzBuzz that you could possibly do, right? So we iterate over the numbers from 1 to n plus 1, and we just check the modulus of them, and we have like a big if, else statement that it falls through, and if it doesn't divide by any of the numbers evenly, it just prints the number. Otherwise, it prints the right thing. So this is cool. Like, this would totally work. If you did this at a job interview, they'd say, great, like you actually can program, good job, you got the job. And it outputs something like this. So like I said, fizz instead of 3, buzz instead of 5, etc. So this, like I said, would have been totally fine. But then I got really interested in super terse programming. And I was like, okay, if someone asks me FizzBuzz in a job interview, I'm going to really wow them. And I'm going to write this thing. So this is a one-liner that also correctly prints FizzBuzz. And I'm not going to explain to you why that works, because honestly, I don't really fully understand what's going on there. So I memorized this, and I was like, this is really going to impress them. But in my imagination, right, there wasn't really even a limit on what language I could use, right? It didn't have to be Python. And so then I got to this point where I was like, okay, maybe I'll learn some really crazy esoteric programming language and really blow their minds with FizzBuzz. So what about Fortran? Could I memorize or learn Fortran and do FizzBuzz in Fortran? It's possible. I mean, people still do stuff in Fortran. What about this language? What if I hammered that out? So if you guys don't know about this language, that would actually implement FizzBuzz in BrainFuck. So I didn't do that. But as great as all of these would have been for my hypothetical interviews, I never really did any of those things. But I was always still really intrigued. When someone asks you to implement FizzBuzz, where do you draw the line? What can and can't you do? Could I make my own language? So if I did, I'd call it DIVSPL. And I'd be like, oh, you want me to do FizzBuzz? I'll do it in DIVSPL. You've never heard of that? It stands for Dustin Ingram's very special programming language. And since it's my own language, right, I can make the syntax anything I want. So if I wanted to make it really easy for myself, I can make it something like this, right? This is kind of the bare amount of information necessary to encode the FizzBuzz problem, right? So I have a range, and then I have 2 words and the number which is they'll replace. And that's if someone tells you to solve FizzBuzz, these are the parameters they need to tell you. And then you have to go and write the code and whatever. But what if my language, like, what if this is all I needed to write, and then it just did it? So this is what I did. I did it in Python, and I have to say that I didn't do it from scratch. This is all sort of on the shoulders of giants. So there's all sorts of tools and frameworks and stuff that can help you also write your own languages. So starting with the most recent one, what I use is something called RPLY, and this is implementation of Ply. Ply is a re-implementation of two really old Unix tools called Lex and Yak. Lex is for lexical analyzers, and Yak is yet another compiler. And so these are all sort of like re-implementations of old tools. And now, so RPly is in Python, and it uses, it actually runs on RPython, which is a restricted subset of Python. And if you guys haven't heard of RPython, it's probably because it's not used for a whole lot. It's mostly used for producing implementations of languages like Python. So if you're familiar with Python, Python is a language, and it's interpreted by a type of interpreter. So you might have heard of CPython, IronPython, which runs on the JVM. PyPy, sorry, that looks terrible. PyPy is self-hosted Python, so that means that the Python interpreter is also written in Python. And that's why the logo is a snake eating its own tail. And in order to do that, they kind of needed to restrict what you can do in Python in order to host the language. So that's what they created RPython for, and it's like a restricted subset of Python. So the reason I'm telling you this, it's not super important, but that's what I did implement it in. And there's some weirdness things that you might notice later when I show you some code. So in Python we have like dynamic typing. So I can have a variable, and it can be a string, hello, and I can reassign it to an integer, and Python doesn't care. Python's like, okay, cool, like now this is an integer. And I can write a function too that takes some parameter, and if it's true, it returns a string. If not, it returns an integer. Python still doesn't care. Like, our functions can return whatever we want. This is, in essence, dynamic typing. But RPython, mostly, it just restricts your ability to arbitrarily mix types like this. So if I try to compile this, and you guys aren't familiar with compiling Python, but it's something you do with RPython. If I try to compile this, I get a union error, the offending annotation. It doesn't like it, right? So you might see some stuff later that looks a little weird, and let's just say it's because of RPython. Okay, so let's design a language. Before we actually write any code, let's sort of think about how a programming language is going to work. And I'm going to show you guys some parallels. I'm not a linguist, but some parallels to written language that might make some of the things we're going to do later more clear. So let's say I showed you this string. But let's say I'm going to show it to you one character at a time, and your job is to interpret what the final sentence is just from those characters. So if I just gave you the letter I, you're going to like, okay, that's the word I. And then I give you the letter S, and you're like, okay, this looks like the word is. And you're going to go through, and you're sort of going to break up the characters into chunks until you get to the end, and you're like, okay, is a woman is in English. That must be I saw a man. And you can sort of like insert those spaces into the character stream. So luckily we have spaces in our language, right? We don't actually have to look at a like random string of characters and try to insert spaces where we think there might be words. So we have spaces, and I can write something like I saw a man eating chicken, and you guys can visualize that, and you know what it looks like. And logically you're breaking these up via white space into words, and each word has different meaning. And these are tokens, right? So all the characters are tokens, white space is tokens, all these are pieces of the language. And we also have expressions, right? We have ways to sort of group tokens, words into kind of themes or ideas, and that's what makes up the language. So this might bring you back to grade school. You can do the like, I saw what? I saw a man. I saw a man doing what? I saw a man eating chicken. And then in your mind, you sort of like parse this sentence, and there's an image in your head, and it probably looks like this, right? But that sentence is kind of ambiguous, right? You could parse that differently. You could group it like this. You could say, I saw a man eating chicken, or you can say, I saw a man eating chicken, and you would have this in your mind, right? So to reduce that ambiguity, we have more tokens in our language, like hyphens. So we can put a hyphen between man and eating, and then it's very clear that I'm talking about like a giant man eating chicken. So these are the steps to interpreting a language, right? We're going to break the characters into individual tokens, like words. We're going to combine those tokens into expressions, which make up sort of individual thoughts or images. And then we're going to evaluate that whole expression, that whole sentence, and it's going to give us like the end result. It's going to give us that mental picture or whatever I'm trying to convey to you. That's what you're going to see. So let's talk about some types of tokens that I'm going to use in DIVSPL. So the first is obviously numbers. So I'm going to say a number is any numeric character, 0 through 9, and they can be more than one together. So these are numbers like 1, 15, 3, and 5. This is a number token. Periods also exist in our language, but I'm going to say that 3 periods in a row is just the ellipsis token. So they're all going to get grouped together. We're going to have words, which is any alphabetical character in a row. So fizz and buzz are words. We have the equal symbol, it has some semantic meaning here. And let's say we have white space too. So there's new line characters. So the first step is to make a lexer. And what the lexer does is it takes that endless stream of characters and it gives us back an iterator in Python, which gives us tokens in the language, right? So so from RPLY, we can import lexer generator and create it. And we're going to start adding sort of like these named regular expressions. So the first one here is ellipsis. I'm going to just call ellipsis. And the regular expression is just 3 periods. A number is any digit 1 or more times. Equal sign is just literally the equals character. A word is A through Z 1 or more times. Because we're super cool, we're not going to care about any white space characters. So any white space token or character is just going to be completely thrown out. And we're also going to ignore comments because we're good developers. And then we'll build our lexer. And we'll have this object called lexer. And I'll show you how it works. So I call lexer.lex with just a stream of tokens, and I get back an iterator. And this is just like a regular Python iterator, so I can call next on it. And what it gives me is it starts to consume tokens until it sees something that it recognizes as, it starts to consume characters until it sees something that it recognizes as a token in our language. So here it consumed the first period, and it said nothing matches for a single period, so it's going to keep consuming periods until it gets 3. And then that regular expression for ellipsis is going to match, and it's going to say, okay, I found an ellipsis token, and it's going to give it back to us. And so it's going to keep, as we call next on it, each time it's going to keep consuming tokens from our language. So the next one was the word foo, so it just kept consuming alphabetic characters until it hit the 4, and it's like, okay, this isn't a word anymore. So here you go, foo. 42, hut, and goes on. So if our stream has invalid tokens, like we didn't define anything that would match against exclamation point, it will allow us to keep consuming characters until it gets to that token that it has nothing to match against. And then it's going to say, whoa, this is a lexing error, syntax error, whatever. This is, you wrote bad code. This is invalid. So here I can just call list on the whole stream, and you can see that I get all of the parts of our DIVSPL implementation back. So number, ellipsis, number, fizz equals 3, buzz equals 5. So that's the first step in interpreting a language, right? We took that stream of characters and we broke it into tokens. So now we just have a list of tokens. The next step is to combine those tokens into expressions. And you can sort of think of this as another pass on the stream of tokens and grouping them together. Like we grouped characters into tokens, we're going to group tokens into expressions. So to do that, we're going to make a parser. And specifically, this is going to be called a look-ahead left-right parser. But all that means is it's going to read from left to right, and it's going to look forwards and see what's going to be there when it matches. So the parser takes the token stream from the lexer, and it separates and it analyzes the tokens according to some set of rules that we're going to define. So let's define our grammar. So here's our implementation again. And what I'm going to do is I'm going to basically draw boxes around different types of expressions. And first they're going to start small. They're just going to be like the integers. So these are all the integers in our language. And I'm going to call these an int box. They're all going to get wrapped in an int box. Words, similarly. And then we're going to start to combine individual pieces into bigger expressions. So this is a range box. A range box is going to have an int box, 3 ellipses, and 15 at the end, or another integer at the end. I'm going to say this is an assignment box. And then in order to sort of be able to collect multiple assignments, I'm going to wrap all the assignments boxes in a single box. So this is assignments plural box. And then I need something that I can just wrap the entire program in, right? So I'm going to say this is the main box, and this encapsulates all the logic of my entire program. And so all the boxes together looks kind of crazy like that. But you can sort of see this tree here, right, where main box must consist of a range box followed by assignments boxes. Assignments boxes consist of a single assignment and more assignments, and keeps going. And then a single assignment can have a word and an int. Range box has 2 integers. So we'll define our boxes. First, I'll do an int box. So from RPly, I'll import a base box, and this is just sort of the class that we're going to inherit from to build all of our boxes. There's 2 things that happen here. First, when it gets initialized, it gets passed the value. And so for the int box, we're just going to set the value to be itself. And the next is I'm going to write just an arbitrary function on this. I'm going to call it getInt. And what getInt is going to do is when I evaluate this box, it's going to return an integer. So it's going to take the value, get the character out of it, and then cast it to an integer. And so if I initialize an int box like this, so I have to give it a token. I have an int box, and now I just have a box. If I call getInt on it, I get the integer 1, right? So you got to see how it went from a string, and now it's an integer. It's a little more complex, but this should make sense as we go on. So a range box. So a range box is going to get 2 tokens, each of the int boxes, and I'm going to set them to be low and high. And then I'm going to write another kind of arbitrarily named function, getRange on it. And what this is going to do is going to return a Python range based on those 2 integers that it was initialized with. So if I, again, initialize a range box like this, I have to give it 2 int boxes, since that's what it needs. And if I call getRange on it, I get the full range here. Next is the word box. So this word box is just a string, like fizz or buzz. So it takes the value, stores it, and when I call getString on it, it just returns it. That's all. So it looks like this. GetString, I get fizz back. So the assignment boxes is when it starts to get a little interesting. So an assignment box is going to get a word and an integer. And when I initialize it, I just set them equal to self.word, self.number. And then I'm going to write another arbitrarily named function called evalWidth. And this is a little bit different because before, all our sort of evaluation functions didn't take any arguments. But this one is going to take an argument. This is going to take the integer I. Okay, so I pass it I, and if I is divisible by self.number, I return an empty string. Otherwise, I return the word that was initialized into an assignments box. So if I initialize the assignments box with the word fizz and the number 3, I can call eval with 40 and I get nothing back. But if I call it with 42, I get fizz back. Okay, that's interesting. And next is the plural assignments box. So this is going to receive a list of assignments, and it's just going to bring them all together. And it's going to basically return a list of all the assignments concatenated together, right? So this allows us to sort of be able to repeat assignments. They sort of nest within each other. Looks like this. And I can call getList, and I can get this a list of single assignments. Okay, that's probably pretty small. So I'll skip ahead. This is just showing multiple assignments in a single assignments box. All right, so the last thing is the main box. And this is going to just sort of encapsulate everything. And what's going to happen is I'm going to get a main box back when I evaluate my programming language, and I'm just going to call eval on it. And that's going to go through and call eval on all of the boxes that are contained within. And then they're all going to come back with a result, and it's going to evaluate the whole program, basically. So main box takes a range and a number of assignments. And then it does a kind of funny thing. And just to explain this quickly, basically it goes through every integer in the range, and then it calls eval with on every single assignment that it knows about and concatenates the results together. So what happens is, let's say we have the number 3 for fizz. If I call eval with 3 on all the assignments, I'm going to get a bunch of empty strings, but one of them is going to say fizz. And so if I combine all those together, I eventually get something that says, empty string, fizz, empty string, empty string, empty string. And then what it does is here it decides to either add of the line that has the word in it, fizz or buzz or whatever, or just casts the int to a string and then adds that together. So that looks like this, probably incomprehensible. Again, here's the parse tree, so we're going to run all the way through it, all the way down to the bottom, and back up to the top to the main box. And so now the last thing to do is define productions. So this is going to take this pattern of tokens and turn it into one of our boxes. So I'm going to say that a range is a number followed by an ellipsis followed by a number. An assignment is a word followed by the equals token followed by the numbers token. Assignments is any number of plural assignments followed by another assignment. And assignments can also just be an empty string, so that's how we can start collecting assignments. And finally, the main is a single range followed by multiple assignments. And so with RPLY, we get a parser generator. We tell about the tokens that we know about. And then we can use this decorator, pg.production, to define production. So this uses the string at the top to say, all right, you see a number token, you're going to generate an int box, pass the first parameter in to that, and then just return it initialized. So that's what the number looks like. The word is similar. A range, so it's going to get a number, ellipsis, and a number. We're basically going to throw out the middle argument. So the P is an array of the arguments, or a list of the arguments, rather. And so the 0th one is going to be the number. The first one is going to be the ellipsis, but we don't actually need that to interpret anything. So we can throw it away and initialize the range box with a number and another number. Assignment is similar. Assignments box is also similar. This is what the empty string looks like. So if it gets an assignments with nothing, you initialize the assignments box with nothing. And then this is the main box. This is where you get a range and assignments. Okay. So then we build the parser. And what we can do is we can take a string of characters, pass it to the lexer, pass what the lexer returns, which is a stream of tokens, to the parser, and then the parser puts it all together and gives us a main box. So we can call .eval on that, and since I only gave it the range 1 through 15, all I got was numbers 1 through 15. So that's step 2, which is combining tokens into an expression. So now we have the expression that we can evaluate. The last thing to do is actually evaluate it. So let's make an interpreter, and this is going to be really quick and easy. So this is kind of a rough approximation. We build a lexer, we build the parser, we open up the first argument as a file, and let's just imagine it's being called with some file name. We read the source from that file. We hand the source to the lexer, which produces the list of tokens. We take those tokens and give it to the parser, which returns an expression. We call eval on it, and then we print the result to the terminal. And that's it. That's the interpreter. That's all it does. Okay, so we did everything. That's what we need to do to create a language. And now let's code. So you guys are in for a treat because usually I just show slides, but I'm going to live code this for you guys. So conference etiquette dictates that you applaud furiously. Wait, not only if it works. All right, let's see if I can do this. All right, so here we are. We're back at live coding. I'm really sorry, guys. All right, so we're going to write a DIVSPL file. So FizzBuzz. So the extension is arbitrary, and we're just going to write text in here, right? So 1 through 15, fizz equals 3, buzz equals 5, not 4. So we write it. We got it, just a plain text file. And so I've bundled up the DIVSPL interpreter, which is the result of all that code put together into something that's pip installable. So you can pip install DIVSPL. And this gives you an executable. So you can type DIVSPL, and it wants file name. So we'll give it fizzbuzz.divspl, FizzBuzz. Okay, so I'll take this for a sec. Let's review. So we wrote this syntax. We got this stream of tokens. We created this massive evaluation tree. we evaluated it, and we got this massive string back with new lines in it. And when that's printed to the terminal, it looks like this. And that's FizzBuzz. So let's take it one step further. This is the basic FizzBuzz problem, right? 3, 5, FizzBuzz. But let's say I'm a really challenging interviewer and I want to make this tricky for you. And I say, okay, in addition to this, you also need to handle the number 7. And if you get to something divisible by 7, you need to print fuzz. So that means if it's divisible by both 3 and 7, you print FizzFuzz. 5 and 7, BuzzFuzz. 3, 5, and 7, FizzBuzzFuzz. Okay? So if we took my super naive example from before, which looked like this, it would get totally out of control, right? So I would just need to add ton more if-else statements that handle all the different moduluses, print all the different strings correctly, and I don't know, it works, so maybe my interviewer would like that, but this looks pretty bad to me. But in DIVSPL, I don't know if I'm going to do live coding again, but basically you can add one more assignment to the line, evaluate that, and it'll handle all of the extensions. Okay, so some questions, and I'm going to preempt a few questions here. Why would I ever do this, right? So that was a lot of work for basically something that's not very useful at all. So yeah, if your question is why would I ever make my own language, this might be a hard question to answer. And it's going to be the kind of thing where you know it when you see it, right? Someday you're going to come across something where you're either Python is not enough for you or Python's too much for you. And then you're oh, maybe I'll make my own syntax and my own language and go from there. And then you're the next Guido van Rossum. But sometimes this is a little more obvious. So I actually didn't have a great answer to this until I met the maintainer of this library called, I learned it's called James Path. And his name is James, which means I already like it because it means he named it after himself. But he does this thing where you can give it sort of this dictionary, and you can say something like foo.bar, and it'll traverse into the dictionary and parse that first query into the data structure, and you can get Baz out. So yeah, this is the James Path website, and in his source code, he's got I don't know if you can see here, he's got a Lexer and a parser. He's not using RPLY, but basically he decided that he wanted to write this sort of query language for James Path, and he did it. That's part of his package that he offers. So another question that I've gotten before about this is, is it faster? Because the title of the talk is the fastest FizzBuzz in the West. And again, this kind of depends on what you mean, right? So if you mean, is it faster to implement FizzBuzz, then yeah, definitely. It's actually, it's going to take you less time. It's less characters, right? It's short enough that you could put it in a tweet and still have room for hashtags and hand claps. And I want you guys to know, I stuck PyTexas in there because I adopted these from previous slides. But maybe your question is it faster to evaluate FizzBuzz? Maybe you came to this talk because you wanted to see some really super high performance FizzBuzzing. And so I'm happy to say that, yeah, actually this is faster. So I did some super naive benchmarks. I took my naive one and ran it 1,000,000 times. And I took my FizzBuzz implementation and took it all the way up to 1,000,000 also. And then I used time to time the Python interpretation of both of these solutions. And this is a little hard to read, but a couple milliseconds faster, I'll take it. That's pretty good. It's the fastest FizzBuzz I've seen yet. So, and so that's it. Thanks, guys. Sorry about the live coding hiccup, and I'll take any questions from the audience. Yeah.
Back on the time, it's compiled, really. So it's apples and oranges, really.
On the time, yes. So the question is, I'm comparing apples to oranges when I'm saying it's faster because it's compiled, and that's correct. So our Python essentially gets compiled into a binary that doesn't get interpreted every time. So in Python, you write a script and you run python script.py, it's going to interpret every line in that script that you need to call in order to get whatever you're trying to do. But with our Python, I've took everything that this does and it's pre-compiled into a binary, so it's not going through the Python interpreter at all. So that's mainly why it's faster. Yeah, but it runs faster. It doesn't compile faster, right? One of the benefits to having Python be an interpreted language like that, you can run it immediately, right? You don't have to wait for something to compile. with RPython, just compiling this takes like 3 or 4 minutes. It's pretty long. So, any other questions?
What are good ways to visualize your abstract syntax tree?
So the question was, what are good ways to visualize your abstract syntax tree? So this is the sort of tree-looking thing that I showed before, where you see, one thing is part of another expression is part of another expression. So for this, I kind of struggled with the best way to show it to people when I'm doing the slides. A tree diagram like that works pretty well, right? Arguably it can get pretty hairy because you can go pretty deep into an abstract syntax tree, right? You have so many different levels, especially for a program like Python, right? It's really hard to see. So I don't have a great answer for you. Because it's a tree, often a tree is the best way to look at it, but you have to look at small parts of it, not the whole thing usually. Any other questions? Yep.
What's like the experience of targeting RPython instead of Python?
Sure. So the question is, what is the experience like targeting RPython instead of Python? And I would say it's something I wouldn't wish on my worst enemy. Especially after being very familiar with Python, it'll basically let you do anything you want. RPython is extremely strict, and it's not designed for people to sort of just start writing Python code in it, right? Like, it's designed for people that are really familiar with the structure of the language. So when it spits out a union error or whatever, it doesn't have great documentation too, because it's kind of designed for language designers and by language designers. So it takes a lot, like very small things trip it up. So you might have noticed that all of my boxes, the arbitrary functions they all had different names, right? I had like get int, get string, get range, whatever. And that's pretty unPythonic to say like get whatever. But it was necessary for our Python because one's returning a string, one's returning an integer, one's returning a range, but they all inherit from the base box. So they all need to have a different name. I can't have 3 functions that just say eval and return different types. So figuring out things like that were pretty hard, and there's a few guides online that can help you with RPython, but generally I'd say you probably don't need to use RPython. Any more questions? Okay. Oh, one more in the back. Scott.
So I think I can imagine for some use case where I might come up with the kind of minimally sufficient information that you packed into the written syntax of your language. What is not at all obvious to me is how I would choose to build that into the structures that you were defining, the various boxes, how the boxes compose, and so on. Do you have any resources or sort of ways of approaching that that are a little structured?
Yeah, I guess the way to think about it is of a dependency tree, right? So in order for me to get a range in my program, I need to have 2 integers first. So that production, like, I have to have the integers first, and then I can define a range based on those integers. So there's sort of like a dependency there, right? Like, integers need to exist first, then I can define ranges using integers. They all sort of like need to consume themselves. You can't have like circular dependencies, right? I can't have it doesn't make much sense, but I can't have an integer that needs a range, and range needs an integer. Like, that's not going to work. So it needs to be kind of hierarchical. I can't say the word. It needs to be in a tree, and yeah. Does that kind of answer the question? Cool. Okay. Thanks, guys.